Philippine GIS Data Clearinghouse by Dr. Al Tongco as the PhilGIS Founding Director for providing a free GIS data for the Philippines, and also grateful for the DUST ERDT for the financial support given, and University of San Carlos School of Engineering for the accessibility and the use of available facilities. So I hope everyone were able to at least have an idea on utilizing agricultural residues in promotion for renewable energy. Thank you very much. I may now entertain questions.
Thank you very much, Ms. Galang. So we do have a lot of questions for you. First, from Dr. Marvin Sinense. What kind of biomass are you considering in your study? Because different biomass have different properties. For example, for if it is rice hull, then it should be your plant should be near the production, must not be near the production area or the farms, but it must be near the rice mill because it is where you get the rice husk for the plant. So again, what is the biomass being considered in your study?
Okay, thank you for the questions. For clarity, the biomass being considered agricultural residues are actually the ones left on the field. So given the identified criteria, so that is the one we try to consider after consultation with stakeholders also that will be utilized for considering for bioenergy.
Okay, thank you. And we also have a question from another panelist. So we have from Mr. Robert Peña. How were the criteria underweights chosen? So actually, Dr. Sinense also has the same question. Um, is there a standard way of doing this?
Okay. So, since the approach is considering multiple criteria, so questionnaires were actually given to people concerned, the people in the municipality, the farmers, the environmentalists, and they were given different selections in which they are going to select on that, and then based on those gathered data, so that's where we started to summarize everything and identify which among of this will be considered for the criteria in as a basis for that study.
Okay, so Dr. Sinense has this comment that he recommends that you use the analytic hierarchical process or AHP because that will help you to compare the relationships between the criteria and then to consider the law of minimum in analyzing the suitability rating. Anyway, that is in the chat box, and maybe later on, Ms. Galang, if you want to address those recommendations and questions, please do so. But
Okay.
we also have questions from our participants in the conference. First, um, this is from Dr. Al Tongko, and also the same question from Mr. Dave Pujadas. Should you include the location of major electrical transmission grids in Bohol as an additional criteria for site suitability of a large biomass plant? Do you think that is important to include?
Yes, actually, as I said, this is an initial phase. The focus is more on the approach, on how to, one way on how to do a site suitability, but it can be considered that there are other criteria that can be incorporated in considering improvement on the methodology for a GIS-based site stability analysis.
Okay, and this is, thank you, and this is our last question. In coming up from Mr. Romel Arubang, in coming up with a suitability map, did you consider the annual yield or harvest of those agricultural feedstocks, particularly for rice?
No, because I only identified four criteria based on the questionnaires that was distributed and summarized. So, production yield was not part of the criteria. Anyway, that kind of data can be utilized in knowing the theoretical availability of agricultural residues that can be used for biomass energy. But since this is focused more identifying site specific, putting up the plan, so those four mentioned criteria in the study were only the ones considered.
Okay, thank you very much, Ms. Galang, for your
Thank you.
presentation.
Thank you.
So we will now proceed with the last presentation. So hopefully we will no longer have any technical problem for this presentation. So the last presentation is titled Investigation of Heat Transfer Efficiency of Tungsten Carbide and Cobalt Oxide Nanoparticles Dispersed on Distilled Water as Base Fluid. So this will be presented by Mr. John Michael I. Marikit from Mindanao State University, Iligan Institute of Technology. Mr. Marikit, can we now have your presentation?
Good morning. Sometime in the early 1980s, a business traveler called a low-cost carrier called People Express to reserve a flight. Unfortunately, he was kept on hold for so long that he thought to himself, either good morning. Sometime in the early 1980s, a business traveler called a low-cost carrier called People Express to reserve a flight. Unfortunately, he was kept on hold for so long that he thought to himself, either this airline is incredibly busy or incredibly inefficient. Needless to say, the flight was never booked and People Express went out of business in 1987. The name of the business traveler was Richard Branson, who, recognizing a great business opportunity when he saw it, developed a more efficient system and went on to launch Virgin Atlantic Airlines. And the rest, of course, is history. The point is, efficiency can either break you or make you. With that in mind, allow me to present to you our research entitled Investigation of Heat Transfer Efficiency of Tungsten Carbide and Cobalt Oxide Nanoparticles Dispersed on Distilled Water as Base Fluid. The thermal properties of heating or cooling fluids play a vital role in the development of new energy efficient heat transfer equipment. However, conventional heat transfer fluids such as water and engine oils have in general poor heat transfer properties compared to those of most solids. In spite of considerable research and efforts deployed until today, major improvements in heat transfer capabilities have suffered a major lacking. As a result, an important need still exists to develop new strategies in order to improve the effective heat transfer behaviors of conventional heat transfer fluids. Now, as metals have higher thermal conductivities compared to fluids, many studies have been made in the past on the thermal behavior of suspended particulate matter. The early studies considered suspension of millimeter or micrometer sized particles, which shows some enhancements, but it has problem of poor suspension stability that cause clogging in systems. With the recent advances in material technology, it made it possible to produce innovative heat transfer fluids by suspending nanometer sized particles that change the transport and thermal properties in base fluids. A solid liquid composite materials consisting of solid nanoparticles with size not larger than 100 nanometers suspended in liquid is defined as nanofluids. With nanoparticles, it showed better suspension stability for it offered greater surface area per mass. And the surface area per mass of a material increases, a greater amount of the material can come into contact with the surrounding materials, thus affecting reactivity. The concept of nanofluid was coined by Stephen Choi of Argonne National Laboratory, USA. and was probably the first to test such fluids. In one of their research, they observed a 160% enhancement in thermal conductivity of 1% volume concentration of carbon nanotubes in engine oil. Another study reported thermal conductivity improvement of 9.2% with graphene nanofluids. Additionally, an improvement in heat transfer coefficient of 193% was observed in their research. A different study reported an average of 25% rise in heat transfer coefficient. As can be perceived, the intensification in heat transfer coefficient in nanofluids parallel to the base fluid can vary from a few percent up to several hundreds of percent. Nonetheless, there are studies where the heat transfer efficiency decreases or there is no significant improvement observed with a supplement of nanoparticles to the base fluid. A study by Williams et al. Revealed no heat transfer improvement. A different setup reported seemingly contradictory behavior of heat transfer deterioration. Another study reported that a grooved heat pipe system with nanofluids led to worse system performance. According to a research by Terekov et al., different data, sometimes contradictory ones, are obtained even for the same composition of nanofluids. Numerous available studies and related literature can be analyzed and cited that shows that there is no quantifiable nor qualitative unanimity with regards to the heat transfer performance of nanofluids. Thus, such circumstance requires additional experimental of the heat transfer of nanofluids, which leads us into laying our objectives for this research. The purpose of this research is to study on the effect on heat transfer efficiency when adding tungsten carbide nanoparticles and cobalt oxide nanoparticles to distilled water at laminar and transient regimes. The study also intends to present a computer simulation of the experiment utilizing SolidWorks flow simulation program and assess whether such method would prove to be beneficial in finding out the effects of the nanofluids investigated. And as many of the study about nanofluids only focus on finding out the effects on thermal conductivity, we set out to evaluate also other thermophysical properties of the nanofluids investigated. Moving on to the methodology, nanoparticles investigated in the study were produced by SAT Nanotechnology Material Company Limited. Tungsten carbide nanoparticles were 99.95% pure. Cobalt oxide nanoparticles were less than 40 nanometers at 99.5% purity. Nanofluids were prepared via two-step method with 0.5% to 2% volume concentration in increments of 0.5%. The mixtures were then placed on a magnetic stirrer for 30 minutes at stirring speed of 1000 RPM. After that, the solution was subjected to ultrasonic vibration for 1.5 hours at 40 kHz. The produced nanofluids were stable for at least 4 hours without any visible sedimentation. Now the rig. The test assembly is outlined with the main objective of investigating the effects or impacts on the convective heat transfer capability of the nanofluid as volume concentration is increased. Nanofluid from the vessel is transported via the pump, passing through the flow sensor and into the shell and tube cross flow with multiple pass heat exchanger unit. Temperature of the incoming hot water will be maintained via an electric heater. Inlet and outlet temperatures of the nanofluids will be verified with the use of Type T and Type J thermocouples with an accuracy of zero point 0.1 plus minus zero point 0.1 degrees Celsius. 16 thermocouples at different points are connected to the data acquisition system. Investigation were done in varying Reynolds number. The simulation aspect of the study will be carried out through the utilization of SolidWorks flow simulation tool. In order to come up with the different nanofluids to simulate in the program, we use the application's engineering database that allow users to create various types of items with defined properties. To create a new type of fluid, in our case a nanofluid, properties such as density, dynamic viscosity, specific heat, and thermal conductivity are needed at least to define a fluid. Such properties were taken from the calculations made using the equations and correlations. Incoming hot water, temperature, nanofluid inlet temperature, hot water mass flow rate, and nanofluid mass flow rates will be taken as input parameters in the simulation, which are based on the results taken from experimental aspect of the study. Now let us move to the findings of the study. Thermal conductivity of nanofluids has an exceptionally prominent part during the heat transfer process, which is one of the main criteria that was considered in selecting of nanoparticles for this study. Figure shows graph results of thermal conductivity of nanofluids at different percent volume concentration against different correlations for thermal conductivity approximations. It can be perceived from the graph results that the thermal conductivities of nanofluids have increased considerably with increasing particle concentration compared to that of the base fluid. Highest increase recorded at 6.02% for tungsten carbide nanofluid and 5.55% increase for cobalt oxide nanofluid, both at 2% volume concentration. Moving on, the figure shows the graph results on the viscosities of the nanofluids compared to approximated results using different correlations. With regards to viscosity, since nanoparticles were dispersed in the base fluid, it developed its resistance to flow, thus increasing its viscosity. Dealing with heat capacity and density, such properties investigated were calculated precisely based upon the mixture rule, which is a weighted mean applied to calculate several properties of a compound matter. The heat capacity of the nanofluids considered were lower compared to that of water. By definition, heat capacity is the quantity of heat delivered to a certain mass of an object to create a unit change in its temperature. With the introduction of solid nanoparticles, which have densities that are greater than the base fluid, this would in turn lead to a heat capacity that is lower than water. Before we discuss Nusselt number results, let us first review the significance of Nusselt number. Nusselt number is the ratio of heat transferred owing to fluid in motion to heat transferred if the fluid was still or motionless. This shows how much the heat transfer is boosted by means of fluid motion. Nusselt number refers to the quality of heat transfer rather than quantity. Thus, one can relate the similar configurations and will still be proficient in evaluating the heat transfer capability. Now let us deal with the Nusselt number of the nanofluids. We calculated Nusselt number based on the results in the test, which is our experimental side, and compared it with the Nusselt number results based on the data from the simulation, and also compared it with a general correlation proposed to estimate or approximate the Nusselt number of a nanofluid, which is considered as the theoretical aspect of the study. As observed, the correlation employed to calculate Nusselt number for the theoretical side does not correspond well with the experimental and simulated aspect. It either undershoots the calculation for both nanofluids with Reynolds number within the laminar condition and overshoots or overestimates the computation with Reynolds number in the transient condition. The same is observed for cobalt oxide nanofluid in terms of discrepancy between the different methods employed to calculate for the Nusselt number, with the theoretical aspect results underestimating and overestimating for laminar and transient conditions, respectively. But for both nanofluids at both regimes, the experimental and simulated results had a better agreement with an average percent difference of 3.85%. Such observations of discrepancy between theoretical calculation and experimental data can also be perceived in a certain study, wherein theoretical calculations undershoot experimental results by 50%. Now, more importantly, let us assess if whether the nanofluids investigated prove to perform better as the cooling agent compared with water. So we employ percent enhancement in heat transfer efficiency. As per evaluation, there was actually a detraction in heat transfer efficiency. For nanofluids under laminar condition, tungsten carbide nanofluids showed no indications of heat transfer efficiency enhancement at any percent volume concentration involved in the study. The trend actually worsens as nanoparticle loading increases, with the largest reduction recorded at 4.89% for 2% volume concentration. Cobalt oxide nanofluid had better results at laminar conditions, recording an enhancement of a high of 4.3% at 1.5% volume concentration. Then at 2% volume concentration, the heat transfer efficiency recorded a reduction of 2.23%. For nanofluids at transit regimes, tungsten carbide nanofluids still has not exhibited any significant improvement in heat transfer efficiency. Nonetheless, the degree of reduction is considerably lower at such regime compared to laminar conditions. For cobalt oxide nanofluid, however, it revealed the best outcomes among all nanofluids in both regimes, exhibiting the highest augmentation of 13.27% at 1.5% volume concentration. A correlation is then proposed for this study to approximate the results of the experimental Nusselt number, where coefficients of the correlation are based on the percent volume concentration, Reynolds number, Prandtl number, and friction factor. But what's it good for? So there's an enhancement, but what then? Allow me to offer some of the applications we could pursue with nanofluids. With the talks of reviving the nuclear power plant here in our nation, such research could explore the nuclear applications of nanofluids in areas dealing with main reactor coolant for pressurized water reactors, or in the area of using nanofluids as coolant for emergency core cooling systems of both pressurized water reactors and boiling water reactors. And how about in the automotive industry? We could explore the possibilities of utilizing nanofluids for cooling systems of our cars, buses, trucks, and so much more. We could also explore the possibility of designing a vaccine storage unit that uses nanofluids to boost or to reinforce in the performance and efficiency of the storage unit. And these are just some of the potential studies I would like to explore in the future if granted the opportunity. Finally, this demands for a more strengthened effort in the study of nanofluids. Compared to the traditional one-sided approach, this research needs to inspect a closely diversity of issues, such as synthesis, as well as system-level applications. Henceforth, a multidisciplinary approach comprising researchers such as thermal engineers, chemical technologists, material scientists, chemists, and physicists needs to be undertaken. Only with such an approach can ensure a cooler future with nanofluids. Thank you.
Thank you very much, Mr. Marikit. Are you now here with us to answer the questions?
Hello, sir.
Yes. Okay.
Good morning.
Good morning. So we have questions first from the panel from
Yes, sir.
Mr. Robert Peña.
Yes, sir.
So this is the question. What were the reasons for choosing the two nanoparticles that you used in your study? What are the advantages?
Yes, sir. Thank you for that question. Actually, there are three types of nanoparticles, which are differentiated by their base. So we have carbon based, we have pure metal based, and we have metal oxide based uh, nanoparticles. Aside from that, we also considered first and foremost the thermal conduct thermal conductivity of the nanoparticles. But what we uh, but as what the results show in our research, it's not just enough to consider the thermal conductivity of the nanoparticle. We have to also look at other thermophysical properties such as the particle density, as well as the concentration, and even the synthesis of our nanofluids. But mainly, the criteria for the choice of those two nanoparticles was their thermal conductivity. Thank you.
Okay. So thank you very much. We have also a question from Dr. Marvin Sinense. What is the difference of your study on the previous studies?
Yes, sir. Thank you for the different the difference compared to other study is that we used a different type of nanoparticle.
So
So
you
this is the
mean
yes, sir. This is the
you
first. Yes, sir. Go ahead.
yeah, so you mean to say that in the literature we
Yes,
do
sir.
not have a study using the nanoparticles that you use for your own research?
Yeah, yes, sir. For there are uh, there are research for cobalt oxide nanoparticles, but with tungsten carbide is the first one.
If like tungsten carbide, these have good thermal properties, why do you think that there were no previous studies on this nanoparticle?
Uh, I so as can be shown by the results, there was actually traction. I think one of the reasons that tungsten carbide was tested because of its relatively higher density compared to other nanoparticles. With a higher particle density, there might be problem, which I think uh, that leads to the diffraction in this study is because of the pumping capacity of the system, because the particle had relatively higher density compared to other nanoparticles.
Okay, so there's a follow-up question from Dr. Sinense. Is the difference significant between theoretical computations versus the result of computer simulations and with the experimental data? I think I have seen in your presentation that there's a 50% difference. So between these three, theoretical, computer simulation, and experimental, so what were the differences obtained, and are these differences significant?
Yes, sir. The one that I've shown about 50% difference was with hello.
Yes, you may continue.
Yes, sir.
Yes.
Can I just pull out the specific numbers for the results, if I may?
Mr. Marikit, if it will take a long time, maybe you do not have to be specific with the actual values, but just the uh, like a discussion on the if there were differences, how significant were these differences?
Okay, sir. I'm sorry, I could not pull out the specific numbers, but yes, there are significant differences between the three methods that was employed in this study. The experimental and the simulation had better agreement because the input parameters that was used in the simulation was based off from the experimental results. Compared with the theoretical, it was just a general correlation to approximate all types of nanofluids. But as I mentioned earlier, there are three types and specifics of nanofluids differentiated by their base. The correlation that was used in this study to compare with the two results that we have in the experimental and the simulated was a general correlation, general correlation for all types of nanofluids. I think that lead to the large discrepancy rather than having a specific correlation for that type or base of nanoparticle.
Okay, thank you very much. Now, this will be the last question from Dr. Virgilio Abellana. How would the nanoparticles affect cavitation problem in the pipes and pumps transferring the said fluid?
Yes, ma'am. Thank you for that question. I actually have not considered the possibility of cavitation, but I think it would be somewhat eliminated by the synthesis of the nanofluids. I think longer periods of uh, exposing the nanofluids to ultrasonic vibration as well as magnetic steering could lead to a more better, how do you say this, better dispersion of the nanoparticles, and would eliminate or but eliminate the possibilities of cavitation. But yes, that's a good area that we could also consider to study.
Thank you very much. Now, in the interest of time, actually, there is still another question on the advantages, aside from cost of using nanofluids. Maybe, Mr. Marikit, you can answer that question in the Q&A box by just typing your answer.
Thank you, sir.
Thank you very much, Mr. Marikit, for your presentation. And for all the presenters in this session on energy, thank you very much for your presentations. I will now turn over the our online stage to our session chair, Dr. Los Visminda Billotendos.
Thank you very much, Sir Bell. I I see that we have had a very interesting first day of presentations, and I hope that the succeeding days will be uh, as interesting as well. Now, with the panelists, we are currently inputting our scores to the Excel file, and in a short while, we will be deliberating. So I don't know how we will agree on this. We are looking at the same tally board. So maybe we will be given, I don't know, Sir Bell, how do we proceed? Because I think I would like to discuss with the other panelists as to the results so that uh, we can announce the best paper for this session.
Good morning, Ma'am Session Chair.
Yes.
Ma'am, we will be demoting the presenters into attendees so that you can discuss and deliberate in the chat room po.
So
Thank you,
you
ma'am.
okay. We're still inputting, so maybe you will give us a few more minutes while I communicate with the other panelists. We're still inputting. We're not yet done for the last presenter. So
Yes, ma'am. Yes po.
okay. May I confirm again, Ms. Secretariat, that there are only 4 of us giving scores?
Yes, ma'am. There are only 4 of you present today po.
Okay. Okay.
Thank
So
you po.
we will now go to the chat box.
While waiting for the result for the best paper to the Secretariat, do we have maybe if there are announcements, or we have a screen while we are waiting showing?
Yes po, sir.
Thank you very much.
So while the panel is deliberating, we would like to thank once again our session chair for today, Dr. Luz Visminda Tindos from the University of San Carlos, our moderator, Engineer Isabelo A. Rabuya, our panelists, Mr. Robert Alfie S. Peña, Mr. Raymark C. Parocha, and Dr. Marvin M. Sinense. We would also like to take this opportunity to invite everyone to join our succeeding sessions, which are scheduled on December 8 to 11. Tomorrow will be the Environment and Infrastructure session, and we will be posting the details on our Facebook page. That's fb.com/ERDT Consortium. Thank you, everyone.
Hello, everyone. I hope everyone's still here. Although I can see already in the participants that we have decreased by about 50. We were quite many just before, but it's okay. It was a very fruitful, productive morning for everyone. But after deliberation or some discussion, not really discussion, but just confirming and ensuring that we have the correct tally, the correct tabulation, we have the best paper for this morning in the energy session. The best paper is presenter number 4, Reniel Rocaverte, with his title, Development of Hybrid Convection Solar Dryer for Seaweeds. Congratulations. Congratulations as well to the rest of the presenters. Actually, by just presenting and disseminating your findings is enough. Although from time to time, we still have to see that someone will become number 1. Now, just to let the presenters and everyone know, there are 4 actually for, how do we say, for criteria for the evaluation. And I think this will be the same for the succeeding presentations. Number 1 is the technical aspect. Number 2 is originality. Number 3 is the commercial viability, the potential for it to be commercialized. Because remember, this is ERDT, Engineering, Research, and Development. And the last one is clarity, how well the presenter disseminated, imparted, articulated the presentation. I mean the findings of the study, and how well questions were answered that were not clear during the presentation, but maybe was more articulated when that same question was asked. Thank you. Sir Bell?
Ma'am, you close the session.
I will close the session.
I think so. Yeah.
Ms. Secretariat, are we going to close now?
Yes, ma'am, please po.
Okay.
Thank you.
Okay. Thank you, everyone, for being patient with our overtime, and for being patient too with the technical problems that we have had, although it was not very long. I would like to thank again our plenary speaker, Dr. Enriquez, and my co-panelists. Please know that we really appreciate the time and the effort you spent in evaluating and grading the paper. It's not easy to read, but here we are with disseminating findings. See you tomorrow until Friday. Goodbye, everyone. Ms. Secretariat, are we leaving now?
Yes, ma'am. Thank you, everyone. Thank you again to
Bye-bye.
our session chair, panelists, moderator, and participants. See you in our future sessions. Thank you.
Tomorrow.
Yes, ma'am. Thank you po.
Sunny day here. Bye-bye.